Hi everyone, my name is Bruno Segura and today I'm in the International Book Fair of Guadalajara, and today I am with Tommaso Calarco, who works at the University of Bologna and studies quantum mechanics and quantum computation. So it's a pleasure to be here with you. How are you?
I am very happy to be here. This is very impressive. This book fair is huge. I just learned that this is the biggest in the world in Spanish language, right?
Yeah, in the Spanish language,
Yeah.
yeah, it is. And the second most important of the world. The other one is in Germany, so it's nice to be here with you.
It's really wonderful, yes.
Well, tell us about how you started your work with quantum mechanics. What was your first approach with this topic?
Oh, well, okay. So my first approach was, I started working with that. It was like 30 years ago because it was completely useless and it was purely philosophical. And there was no idea whatsoever that this would ever lead to any technology. Okay. And it was philosophical almost in the sense that it had to do with questions such as, does reality exist locally, and other very funny things. So, I mean, there was no expectation to be able to make computers or communication devices or anything like that. It was just because I was fascinated. It was purely out of curiosity, I could say.
Okay, and how does the quantum computation start? How does it start the idea that it's possible to do something atom by atom?
Well, okay, it starts from two sides. One is being indeed able to manipulate individual atoms. So one of the inventors of quantum mechanics, one of the founders, Erwin Schrödinger, said once, sometimes we think we can experiment with individual atoms, but this is ridiculous. You know, every time you say this, it has consequences which make no sense. It would be much more sensible to imagine that you can raise a pterodactyl in a zoo. And now nobody knows why he chose the pterodactyl as opposed to something which is easier to pronounce, okay? But the idea was, I mean, this is ridiculous. It makes no sense whatsoever. Yeah. And so for many, many years, you know, even the top scientists working in quantum mechanics, they thought, okay, I mean, we can think about working with single quanta, but doing it, it's never going to happen. Yeah. And then what happened, I would say maybe already in the 80s and then more in the 90s, was that people were able to work with single atoms, single photons, single electrons. And so it became feasible what, everybody had thought until then that it was impossible. And so this is where it came from the really experimental, the material side, the really physical side. And then once you can do these things, you can manipulate individual atoms, you start wondering what you can do with that. And then from the entirely different side, this came from some reflection about, what is it that we can compute, what are the limits, what is the possibility to compute the most difficult things. And some of the most difficult problems are problems in quantum mechanics, because those are very, very difficult to calculate. And so here was instead a theorist, a theoretical physicist, Richard Feynman, one of the greatest of last century, which said, if we had a quantum mechanical system, like a device which would be working and calculating based on the laws of quantum mechanics, maybe we could solve those problems, we could reproduce, we could calculate, not by classical means, not with a standard computer, but with a really quantum device, the properties of such devices. And then he invented the idea of the quantum simulator, which is a special type of quantum computer. And when people started, manipulating individual quantum systems, such as individual atoms, they realized, maybe this is the moment in which we can realize this dream. And so things started to grow together, and this has functioned in this way for the last 30 years, bringing us to now being able to buy even some of those machines.
Yeah, there are some elements on quantum computation that are the qubits. Those we're used to the bits that are or a 0 or a 1, but in the qubits there are 1 and 0 at a time. So how do they work?
Well, they are very delicate, so you have to isolate them from everything else. And once you isolate them, then they start behaving with this, which is called the superposition. So they start obeying the laws of quantum mechanics, which means indeed that they can be an object can be in two possible states at the same time. So it could be an electron, and an electron is a very little magnet. It could point upwards or downwards, or maybe in a combination of both. And now if I give values 0 and 1 to those two possibilities, then we start seeing that this bit will be in a superposition, having the same at the same time both possibilities, and maybe even not just half and half, or maybe 70%, 30%, so all different possible combinations. And now if you have many of these qubits, you can write on a string of those qubits, you can write all possible values of numbers which you could represent. Like if I have a megabyte, I can write, just take it, I have a memory for 1 megabyte, I can write one picture of 1 megabyte, one photo. If instead I had a mega qubite, so like a million of qubits, then I could write all the possible pictures. I could save all possible pictures ever taken with one, just in one go. Then of course the problem is when I look at them, I will see only one. So, the problem of a quantum computer is to be able to manipulate these states of many quantum bits in order to get an answer to some problem, only at the end. Because if I look in the quantum computer while it is functioning, in which there are all these possibilities, then it will collapse, and I do not find the solution. So this is the big challenge that we have with quantum computers.
And how do you think quantum computers could work in the future and be useful to us? You said that in the start this was something useless and just a philosophical problem, but how could they be applied in the future?
Right, so there are some problems for which we know that if we use all these superpositions, during the computation the computer is sort of trying all possible solutions, then this allows us to get to the solution in a much quicker way. There are a few problems for which we know that this is the case. One is a problem which is about factoring, finding factors, so two numbers, which when I multiply them one by the other, I get another number which is given in the beginning. And this seems a very kind of boring mathematical problem, but it has a lot of applications, especially for instance in the security of data communication. Because the way in which we can protect, we can encrypt, we can encode, something like our credit card number, which we want to be kept secret when we send it over the internet, is exactly by multiplying it with some unknown number, and then we can transmit it, but it cannot be decoded only by someone who has the key to decode it. So now instead, a quantum computer which is able to invert, so to solve this, finding the factors, could find the factors and could find our credit card number, from the bigger number which is transmitted, and could decode, decrypt. So the security of communications which are nowadays on the internet would be very much in danger. So this is one, let's say, potential negative application, if you wish, because it would, sort of be a problem for the security of our communications. But on the other hand, there are other things such as, searching a certain data in a big database, where also a quantum computer can give a big acceleration, and applications of this allow to search for the minimum of a function, and this is something which is very much used in artificial intelligence. And so in the long term, but we are speaking about 15, 20 years from now maybe, there could be the possibility of using such devices, for instance, to make much, much faster artificial intelligence and machine learning.
Okay, and which are the biggest problems in this time to work in this quantum computation?
The biggest problem is that, these qubits, I said before, in order for them to work in this way, that you have 0 and 1 at the same time, you have to isolate them very well. And so, this becomes more and more difficult if I have more of them, because I want that they stay in this superposition of all possibilities at the same time. However, I also want, if I want to use this as a computer, I needed to sort of read out. I needed to tell the computer, now do this calculation, do this other calculation. So it cannot be completely isolated. Essentially, I want all these qubits to listen just to me and not to anything else in the universe. So this is very difficult. It becomes more and more difficult the more qubits we have. This is the problem, which is called the scalability, scaling up with a large number, which is necessary in order to run proper computations. At the moment, the maximum number of qubits that we have is a few dozens, you know, maybe about 100, maybe maximum 200, but with some limitations. And so we would need many millions in order to really, use them to calculate something useful. So this is a huge problem in engineering, because we have to, make these systems in such a way that you can, on one hand, control in this quantum way many qubits, but on the other hand, that they are very well preserved so that they do not lose their quantum properties. So this is the main difficulty that we have today.
And which part of this work with quantum computation are you doing now?
Well, at the moment, we are in our research center, for instance, in Jülich, Germany, which is Germany's biggest national lab. What we are doing is we start really from the materials, and then we do the fabrication of small circuits, because we focus in that case on semiconductor and superconductor quantum computers. And then what I do in my institute is really I try to develop methods to guide, to drive, to control these qubits in a way that they do the calculation that we want. And then once we are able to do that, we have to find out new algorithms, new methods to make calculations which are efficient. So there is really what we call a full stack. So it's really a big pile of many layers, and on top there are some problems that we want to solve and some quantum programs, some quantum software that allows to solve them. And below that there is the translation, so-called compilation, translation of these problems into really which physical operations, what do I switch on and off in my quantum computer. And then if we go one level below, we are seeing how we better switch on and off, in order for this to be very quick, very efficient, with no errors. And then as we go down, we have to make these systems in a way that they are very robust, that I can have many qubits, and that I can isolate them, as I said before. So in all of these levels, we are working in my institute, in our research center. And what I do specifically is, making theories to control really how to steer these devices towards the goal of the algorithm.
And how much time do you think that in the future we will reach to this useful quantum computation?
So, well, I think that someone, maybe it was Winston Churchill, maybe it was someone else, they said it is very difficult to make a prediction, especially about the future. Yeah. And so it's very difficult because if we are scientists, we can only speak about what is known. And well, in this case, it's uncertain. We don't even know that we will be able to produce those many millions of qubits. So maybe the answer is never. That would be the worst. But on the other hand, we have had such a development in the recent years that actually it has developed more quickly than we thought, so that it's actually possible that we will find a solution. But for these many millions of qubits, nobody expects them to be available within 10 to 15 years, probably more. Okay, so it's really it's not like a sprint race, it's more like a marathon. Yeah. And so this is really long term, and this is important for everybody to understand, because it is some investment which is required over these many years without being able to expect that I will have results tomorrow. So that's a big challenge, and many people are working about this worldwide.
Oh, well, this is something that in the history of science we've saw that some results, it's really difficult to get them. So, as you said, it's really slow. But in the meanwhile, there is no theory that says that you can't do it, right?
That is correct, yes. In fact, we didn't know this because up until maybe 20 years ago, we didn't know because there are errors. I mentioned this fact that we have to do qubits operations with the smallest possible errors. up until maybe 20 years ago, we didn't know whether in the end this presence of errors would invalidate, would prevent us from doing a big quantum computation. However, we have also developed a theory of error correction, so that now we know that there are ways to make a functioning quantum computer, even building of many different parts which are per se not perfect. So once we know this, we know that there is no scientific obstacle, no fundamental obstacle, as you are saying, so it will be possible in principle, and so it becomes a question, will we be able to make those devices which will have the sufficient quality? But yes, it's a question which is no longer, there are no longer roadblocks or obstacles.
Yeah.
We know in principle it's possible, and now we have to make it happen in reality.
Okay, and let's don't talk only about a quantum computation, but about also a quantum internet. Is this possible? How would this work?
Well, this is a very important question, which is related to another property of quantum mechanical systems, because our qubits, not only they can be in this superposition, as we said before, which is useful for computing, but also they have one important, we could say, limitation, which is, as I mentioned before, if I observe them, if I try to see what is the status, then I change it. It collapses. So what happens is that, this, on one end, it's a problem because it's a difficulty. We have to be more careful when we deal with them. On the other hand, it's an advantage, because if now someone is trying to intercept a message, so an eavesdropper is trying to get, the information that we are trying to send, then it will be possible to notice this. So it will be possible to see, okay, this qubit has been sent, it has arrived, and now I know that nobody has tampered with the communication channel. Or if someone does, I know that this is not a reliable qubit. So it means that we can create what is known as quantum cryptography. We can distribute some secret numbers which only the sender and the receiver know, even over long distances. At the moment, maximum several hundred kilometers, but in the future it can be extended much beyond. And so this is the basis for secure communications. Now, if we will connect, quantum computers with these communication channels in which I take some of the qubits and I send them, from one computer to the other, then this will be the basis of a quantum internet, which will be able to extend the range of secure communications. Also, it will enable the use of quantum computers remotely, in the sense that you could even do a calculation on a remote quantum computer without anybody knowing what you are calculating. Imagine, let's say, a company, someone who has a problem which they want to solve, but they don't want anybody else to know about what the problem is. They will be able to run it on a quantum computer from a distance, maybe combining different quantum computers as nodes of the quantum internet, and then this will enable, much broader applications. So this is, on the other hand, something which is going even beyond the time scale that I said before, because first we have to develop those quantum communication channels, and there are already some devices that you can buy. Then we have to develop those quantum computers which will work with many qubits, as we said, and then we'll be able to connect them in what could be a future quantum internet. So this is a very long time dream, but again, it is something which is thinkable, and perhaps we will live to see it.
And how is this related to what Einstein said about this spooky act at the distance?
Yes, so Einstein was saying that there is this spooky action at a distance when talking about entanglement. Because entanglement is one property which you have if you have more than one particle. If you have, for instance, two, if they are in this superposition state, that we said before, maybe, both could be 0 or 1. But then they could now also be together in a state 0, 0 plus 1, 1. Meaning, if I measure one of them, even if they are very far away at a large distance, let's say that one person here measures one of the qubits which are entangled, and then another person, the other qubit entangled, let's say we gave it to someone else in Ciudad de Mexico. And then this person will measure also their qubit. And the person here in Guadalajara, when they measure it, will know immediately, since it was 0, 0 plus 1, 1, but no other combination, if they find a 0 here, the person in Ciudad de Mexico, they will find 0, and vice versa. So this is really something which works over a long distance. It enables also teleportation, which is something which was realized by last year's Nobel laureate Anton Zeilinger, and this is something which is really a paradox. It's actually unbelievable in the sense that we humans cannot build a mental image of that. And so this is why Einstein said this was spooky, because he thought that this made no sense, and actually that quantum mechanics was wrong. But in fact, he was proven wrong because Alain Aspect made the experiment, and he also got a Nobel Prize last year for that, which demonstrated that indeed this entanglement exists and can give rise indeed to some correlations at a very large distance.
Yeah, at first sight, this is something like unnatural, right? This is something like it may violate the light cones, but it doesn't, right?
It doesn't, and the reason is the following. Because, it is true that, the person here in Guadalajara, they know what the other person in Ciudad de Mexico will find, but the person in Ciudad de Mexico does not know. So does not know that the measurement here has been performed. And in order to sort of be able to connect the two sides, also to do teleportation, for instance, there needs to be some communication, like at least, the person here has to call via phone the person there. And this can only happen at maximum speed with the speed of light. So there is nothing which is going beyond the speed of light, but still, this correlation is there, and the change in the state happens. You can check if you measure at the same time that this correlation is always there. And so this is something which is indeed, as you say, kind of unbelievable or really, very mysterious, one could say. Yeah.
Well, thank you very much, Tommaso, for giving the time to this interview. It was a really pleasure to be talking with you. So thank you very much.
Thanks a lot, and also for me, it was a great pleasure. Thanks a lot.
Thank you. Thank you also, our public, for watching this interview, and follow us as Polimateando.